Hello students, welcome to today's class. In today's class, we will be dealing with the topic of hypothesis testing, which is in fact the basis of experimental research. Any kind of experimental research begins with the formulation of the hypothesis. Once we have identified the independent variable and the dependent variable, then comes the stage when we have to formulate a hypothesis. Now, what is a hypothesis? A hypothesis is nothing but a testable statement or a testable proportion or a testable proposition or a testable potential solution to the problem. Say for example, we have two variables, an independent variable of reward and a dependent variable of learning. So we need some kind of statement that is a relation or a proposed relation between reward and learning. And hence our hypothesis may be that reward improves learning. So we are giving a potential statement or a potential relationship between reward and learning. And this statement is testable, which means that when we put forward a hypothesis, it is not a solution. It is a statement which should be tested so as to find the solution. When we say reward improves learning, we will again test this statement, and either we will find that the statement or the hypothesis is right, indeed reward improves learning, or we may find that the statement is wrong, reward does not improve learning or has no effect on learning. So in any way, formulation of the hypothesis is the basic step of research, and research can go forward only once we have a hypothesis in place. Now there are certain things to be kept in mind while formulating a hypothesis. The first point is that a hypothesis should be conceptually clear. When you read a hypothesis as an experimenter or others read your hypothesis as subjects or as other observers, we should have a clear understanding of what kind of relationship is being proposed between the independent variable or variables and the dependent variable or variables. For instance, reward improves learning is an example of a conceptually clear hypothesis because there is no scope of doubt. We know that the hypothesis says that there is a potential relationship between reward and learning, and it is a positive relationship, that is, reward improves learning. A second factor is that a hypothesis should be testable. A hypothesis, as we know, is not a solution. It is a statement which should be tested to bring out the solution to the experimental question, and hence the hypothesis should be such that we can actually test it with the kind of instruments or with the kind of research methods that we have. If we cannot test the hypothesis, then the hypothesis becomes useless for us. A third factor is that the hypothesis should be economical or parsimonial, which means that testing the hypothesis must be within the budget of our research. If the hypothesis is very complex or the testing of the hypothesis requires a lot of money, then it may not be feasible for us to go ahead with the hypothesis. Another factor is that the hypothesis must be related to existing body of research, theory and facts. You cannot just bring a hypothesis out of the blue. For instance, if a researcher puts forward a hypothesis that skin color influences intelligence, of course it may look like a very interesting hypothesis, but it has no kind of research basis or no kind of theoretical basis, and hence in most cases testing of that hypothesis won't be very useful and will not put forward any kind of useful results. Thus, as far as possible, hypothesis should be based on an existing body of theory, facts and observations, or even if the experimenter is putting forward an entirely new hypothesis, it must be based on some kind of systematic analysis of the situation and a systematic understanding of what kind of relationships may exist between variables. As we have already mentioned, another important factor is that a hypothesis must also be logical and comprehensive. Another factor is that the hypothesis should not be too general in scope or too specific in scope. If it is too specific, then the entire problem becomes too trivial. On the other hand, if it's too general, then it may not be able for us to actually test all aspects of the hypothesis and bring together the results in a way that can be understood or can be useful. And finally, a hypothesis should be related to the available tools and techniques we have for investigation. If we bring in a hypothesis for which we cannot actually design a plan or we cannot actually have the necessary tools and instrumentations for testing, then it will never be possible to test that hypothesis, and the hypothesis will remain in the shelf and it will never become a part of active research. Now we will be quickly going over what are the different types of hypothesis. We will be going over some main types of hypothesis. The first is the simple hypothesis. Now the simple hypothesis explains a proposed relationship between either one or two variables. If we take the hypothesis we were discussing till now, that reward improves learning, this is an example of a simple hypothesis because there are only two variables, one is reward and the other is learning. Also, hypothesis can be a complex hypothesis. In a complex hypothesis, there are more than two variables and the relationship between more than two variables is being expressed. And the proposed relationship between more than two variables is being expressed. For instance, if we say that children from middle and lower economic backgrounds have a lower level of intelligence as compared to children from higher economic backgrounds, we can see that there are a number of variables involved. Economic backgrounds modulated in three ways, and then we are looking at the intelligence of children, and hence it is not a simple hypothesis or a simple relationship or a simple proposal of relationship between one or more variables. Then we come to an all-important type of hypothesis, that is the null hypothesis. The null hypothesis is also sometimes called the no effect hypothesis or the negative hypothesis. It is an opposite of the research hypothesis. The null hypothesis states that there is no relationship whatsoever between the variables under question. So it will say that there is no relationship between reward and learning. Now, null hypothesis is basically a hypothesis which the investigator wants to disprove, or he wants to prove that the null hypothesis is wrong in most of the cases. So when the null hypothesis is proved wrong, what is proved right is the next type of hypothesis, or the alternative hypothesis. Now, alternative hypothesis proposes all possible types of relationships between the two variables or between two or more variables except that proposed by the null hypothesis. Thus, alternative hypothesis may say that reward improves learning, or reward leads to lesser amounts of learning, or any other such proposition, but not the null hypothesis proposition that there is no relationship between reward and learning. So, when the null hypothesis is rejected, automatically it means that there is some kind of alternative relationship, either a positive relationship between reward and learning or a negative relationship between reward and learning. And this alternative hypothesis is what the experimenter basically wants to prove in the course of the experiment. Now we'll be dealing with one important concept that we need to understand while we are dealing with the concept of hypothesis testing, and this is the significance level. Whenever we hear about experiments, we hear researchers saying that they have seen that there is a significant difference between certain variables, or there is a significant impact of one variable on the other. How do they say so? They say so because they have tested their hypothesis and accepted it or rejected it at some level of significance. So then it becomes necessary for us to understand what is the level of significance. Now usually we say that we have 0.05 level of significance or a 0.01% level of significance. Now what does it mean? For example, if we are rejecting a null hypothesis at a significance level of 0.5, it means that there are 5 chances out of 100 that we are rejecting a hypothesis which is in fact true. That is, there are 5% chances of error in our judgment. That is why most psychologists and experimenters strive for a higher level of significance, that is the 0.01 level of significance. It means that when we are rejecting a null hypothesis at a 0.1 level of significance, it indicates that there are only 1 chances out of 100 that our rejection of the null hypothesis is an error, or that we are rejecting a hypothesis which is in fact true. Now, when we are dealing with the significance level and the rejection of hypothesis, we come to another important concept that we need to learn today, that is type 1 error and type 2 error. When we reject a null hypothesis, when in fact it is true, it constitutes a type 1 error or an alpha error. On the other hand, if we accept a null hypothesis as true, when in fact it is false, it constitutes a type 2 error or a beta error. Now we try to reduce the type 1 error by increasing our level of significance possibly to 0.1, to 0.01 or 0.001 or any higher level, so that our possibility of rejecting a hypothesis when in fact it is true becomes less. But as we try to reduce type 1 error, our chances of committing a type 2 error increase, which means we move closer towards accepting a hypothesis which is in fact false as true. And hence, thus, when we try to reduce type 1 or alpha error, we move towards type 2 or beta error. Now, when we go forward and test a hypothesis so as to answer the research question that we have in hand, we may use two types of statistics. One is the parametric statistics or the standard tests of hypothesis, or the non-parametric statistics or the distribution-free tests of hypothesis. First, let us deal with parametric statistics or the standard tests of hypothesis. Now, parametric statistics are seen to be the most powerful tools for testing a hypothesis, and hence most experimenters prefer to put to use parametric statistics when they are dealing with their research problem. But however, before we employ a parametric statistic, certain conditions regarding the population and regarding the sample must be fulfilled. If it is not fulfilled, we cannot go ahead and use a parametric statistic. Let us have a brief overview of what these conditions are. The observations regarding each case must be independent, or the selection of one case should not be dependent on the selection of the other case. A second important condition for application of a parametric statistic is that there should be a normal distribution of a population. I think we all must know what a normal distribution is. When a population is normally distributed for any characteristic, people in the middle of the normal distribution curve, or a majority or a large number of people, have moderate levels of that characteristic, whereas there are extreme cases who have either very high levels of the characteristic or very low levels of the characteristic. This is the normal distribution of the population with regard to any characteristic or attribute. And parametric statistics require that the population from which the sample is drawn is normally distributed. A third criteria is that the variables or the scores should be put forward either in interval scales or ratio scales. Nominal scales or ordinal scales, that is frequencies or rankings, cannot be used when we are employing a parametric statistic. Another requirement for the employment of parametric statistic is that the variables must be continuous, or we must be able to divide the variables to any arbitrary degree or any arbitrary measure. Another assumption required for the employment of parametric statistics is that of the homogeneity of variance. The homogeneity of variance in short means that the sample or samples must be drawn from a population where variances or means and standard deviations are equal. Thus, we know that to employ a parametric statistic, we must fulfill 5 major conditions. First, the continuity of the variables. Second, that the variables must be expressed either in interval or ratio scales. Third, a guarantee of the normal distribution of the population. Fourth, guarantee of the independence of observations. And finally, a guarantee of the homogeneity of variances. But the thing is that in real life, many a times we may not be able to fulfill all the various conditions required by a parametric statistic. And hence, we often resort to the use of non-parametric statistics or distribution-free statistics in our research. Now, non-parametric statistics can be mainly used when the sample size is small, when the scores are represented either in the nominal or the ordinal scales, that is in terms of frequencies or rankings, and also when we do not have any knowledge as to whether the population is normally distributed or not. Now, first we will be dealing with 4 important types of parametric statistics. The first parametric statistic we are going to deal with today is the t-test. The t-test was developed in 1915 by William Seeley Gossett, who was the statistician for Guinness Breweries in Dublin, Ireland. Now, because the research code prohibited the publication of the name of the person who actually developed the statistic, he simply signed it off as student, and hence today we refer to the t-test also as the student's t-test. Now, the main function in simple terms of the t-test is to test the significance of the mean differences between 2 sets of scores or 2 sets of samples. Thus, in other words, we are testing whether there is a significant difference between the means of two sets of scores or two sets of measures. If the scores or the samples are related in some way, what we can use is a paired t-test. Now, the t-test is mostly used when the sample size is not large, that is, it is less than 30. When the sample size exceeds 30, then we use the z-test, and this is another major form of parametric statistics. Now that we have seen the t-test and the z-test, we move on to the f-test. This is also called the analysis of variance or the ANOVA and was developed by R.F. Fisher. Suppose we want to find out whether the mean differences of more than two sets of scores are significant or not, then it becomes problematic to use the t-test. Say for example, we have 5 sets of scores, we almost need to use 10 t-tests to find out whether the mean differences of these scores are significant or not. In such cases, it becomes useful to use the f-test, because the f-test allows us to understand and to pinpoint significant mean differences between multiple sets of scores or more than 2 sets of scores. Now, another advantage of the f-test, which the t-test cannot achieve in any circumstances, is to understand the effects of interaction. Not only does the f-test allow us to see whether the means of different sets of scores have significant differences. Now, one major disadvantage with the f-test is that we can see whether there are significant mean differences between, say, 3 variables A, B and C, but we cannot pinpoint as to what the differences are. If we want to pinpoint as to where the differences or what the differences are, advanced statistics. Now, another type of parametric statistic we are going to see very briefly today is the Pearson's product moment correlation. Now, Pearson's product moment correlation was developed by Carl Pearson and is also known as Pearson's R. It is used to assess the extent to which there is a relationship between two variables, say variable x and variable y. Now, this correlation ranges between -1 through 0 to +1. +1 indicates a perfectly positive correlation, -1 indicates a perfectly negative correlation, and 0 indicates an absence of a significant correlation. Now, for example, we want to know whether there is any kind of relationship between intelligence and creativity, and we get a score, say, of 0.90, this indicates that there is a highly significant correlation between intelligence and creativity, and since it is plus 0.90 or 0.90, the correlation is positive, which in other words means that when intelligence increases, creativity also increases. However, on the other hand, say suppose we get a correlation of minus 0.90 between intelligence and creativity. Of course, the correlation will be significant because the sign does not make any effect in the significance of the correlation, but the sign indicates that the correlation is negative, which means that when intelligence increases, creativity will decrease. On the other hand, if no significant correlation is obtained, we can say that there is no significant relationship between intelligence and creativity. Now, one major limitation we should remember about all correlational methods, whether it is Pearson's R or any other correlational methods, is that they do not put forward in any way any sort of cause and effect relationship. Just because intelligence and creativity have a significant positive correlation doesn't mean that creativity is caused by a high intelligence or intelligence is caused by a high level of creativity. We can only say that these two variables are highly related to each other. Whether one causes the other or not is to be found out with other advanced statistical techniques or techniques apart from correlation. Now, there are two other necessary conditions that need to be fulfilled if you have to apply Pearson's product moment correlation. The first is that the relationship between the two variables, say x and y, must be linear. And the second assumption is that of homoscedasticity or equal scatteredness or like scatteredness, which in other words means that there should be an equal scatteredness or variance of the distribution. Now, if you have a look at a picture, you will see that figure A shows a figure which is linear but non-homoscedastic. Picture B also shows a figure which is linear but non-homoscedastic, and the third figure shows a relationship which is both linear as well as homoscedastic. Now we come to non-parametric statistics. Non-parametric statistics, as we have already discussed, are called distribution-free statistics, and many researchers prefer these statistics because they can be applied more speedily and a lot of conditions or assumptions regarding the population need not be fulfilled, and hence they can be applied more easily. However, it is best to use non-parametric statistics when the sample is small or when you cannot fulfill all the assumptions needed to apply a parametric statistic. Now today we will be discussing 7 non-parametric statistics. The first is the Chisquare test. Now the Chisquare test was also popularly known by Guilford as the general purpose statistic because it is used for a number of purposes. Now, as any other non-parametric statistic, application of the Chisquare test does not require any kind of assumption regarding the normalcy of the distribution or the homogeneity of the variance. Basic assumption is that the scores or the measures should be put forward in terms of frequencies and percentages, and that the Chisquare test deals only with discrete data, and the data, if it is in any other form, should be converted into frequencies or percentages before the Chisquare test can be applied. Now the Chisquare test is applied for a number of purposes. The first is to test the equal probability hypothesis. Say for example, you are giving a test to 100 students, and this test consists of multiple choice items. There are 5 choices. For instance, it includes 5 items: strongly agree, agree, neutral, disagree, and strongly disagree. So basically, if the equal probability hypothesis works, we will expect that out of the 100 students, 20 students will answer each of these options. For example, 20 students will answer in neutral, 20 students will answer in agree, and so on. So whether the pattern of answering or whether the pattern of any other such measure follows the equal probability hypothesis is checked by the Chisquare test. Another duty of the Chisquare test is to check the normalcy of the distribution of characteristics in the population. Chisquare test is also used to analyze the significance of other statistics such as phi correlation or the correlation of concordance. Another use of the Chisquare test is to check the independence of variables, or whether the different variables are independent of each other or are not dependent on the effects of the other. A second non-parametric statistic we are dealing today is the MannWhitney U test. Now the MannWhitney U test can be simply seen as a non-parametric substitute of the t-test, because the MannWhitney U test also focuses on analyzing the significance of the mean difference between 2 independently drawn samples or groups. Now one condition is that this measures should be in rank order or should be in the ordinal form, and if the measurements are not in the ordinal form or not in the form of ranks, then they have to be converted to ranks before the MannWhitney U test is applied. Often this test is used to see the various ranks given by different experimenters or different observers to a particular situation. A third type of parametric statistic we are understanding today is the rank difference method, and it includes 2 methods, that is the Spearman's rank difference method and the Kendall's rank difference method. Now rank difference methods are non-parametric statistics which basically try to find whether there is a significant correlation between 2 sets of ranks, and data has to be either presented in terms of ranks or has to be converted into rank form before the Spearman's rank difference method or the Kendall's rank difference method can be used. Now just for your information, the Spearman's rank difference method is also called the Spearman's rho, that is RHO, and the Kendall's rank difference method is also known as the Kendall's tau or TAU. Now Spearman's and Kendall's rank difference methods can be used to assess the correlation between 2 sets of ranks. Now when we have more than 2 sets of ranks, what we use is the coefficient of concordance, which is symbolized by the symbol W. Now the coefficient of concordance assesses the significance of the correlation between more than 2 sets of ranks, and of course the data has to be presented in the form of ranks. One major feature of the coefficient of concordance W is that the correlation is either 0 or positive. It cannot be negative. Now we come to another parametric statistics, that is the median test. Now the median test tries to find out whether the scores or the measures or the samples have been derived from a population having the same median. Now the null hypothesis here is that there is no difference between the two set of scores because they have been drawn from the same population or the population having the same median or midpoint. Now if the median test confirms this null hypothesis, it means that exactly half of the scores in each of the two sets of scores will lie above the midpoint or the median, and half of the scores in both the two sets of scores will lie below the midpoint or below the median. Now we come to the last two parametric statistics, that is the KruskalWatts H test and the Freudman test. Now the KruskalWatts H test and the Freudman test are actually non-parametric correlates or non-parametric substitutes of the parametric F test. Now in the F test, one major point is that an F test can either be a one-way analysis of variance or a two-way analysis of variance. When an ANOVA is a one-way analysis of variance, there is only one independent variable, and that one independent variable may be manipulated in a number of ways. In a two-way analysis of variance, there are two or more than two independent variables and they are manipulated in a number of ways. And hence the KruskalWatts H test is a direct non-parametric substitute of the one-way analysis of variance where there is only one independent variable. And the Freudman test is exactly a non-parametric substitute of the two-way analysis of variance or the two-way ANOVA, where two or more than two independent variables and the significant differences between them can be analyzed. Thus we can see in this chapter that we learnt why hypothesis is a necessary and basic aspect of research, and then we understood some important concepts such as the level of significance or the concept of type 1 and type 2 errors in the process of hypothesis testing. Finally, we understood what are the standard or parametric means of testing a hypothesis, under which we learnt about the t-test, the z-test, the f-test and Pearson's product moment correlation or Pearson's R. Then we came to the distribution free or non-parametric tests of statistics, in which we learnt about 7 non-parametric tests, that is the Chisquare test, the MannWhitney U test, the rank difference methods, the coefficient of concordance, the median test, the KruskalWatts H test and the Freudman test.